Welcome to the next session, my dear friends. In the previous session, we were discussing about the rectangular type continuous flow sedimentation tank. Different terms we are discussing. So, in this session, we are starting with the factors affecting the efficiency of sedimentation tank. Factors affecting the efficiency of rectangular type sedimentation tank with the continuous flow. Factors affecting efficiency of sedimentation tank. Sedimentation tank. See, what is the formula of efficiency? So, the formula of efficiency is eta is equal to Vs by V naught into 100. See here, Vs is the property of the particle. Vs is the property of particle. So, we have no control on the particle properties. So, we cannot control the kind of particles that needs to be entered into sedimentation tank. We cannot have any kind of control on the property of the particle. Any particle may enter into the raw water. That particle may enter into the sedimentation tank. We have no control on Vs. But where we have control? Sedimentation tank is constructed and designed by us. So, here this is the factor which we can control. V naught we can control. So, generally V naught is the location where we can where it affects the efficiency of the sedimentation tank. So, now here V naught is equal to Q by BL, isn't it? V naught is equal to Q by BL. So, if Vs is not controlled by us, so remove it. So, efficiency is inversely proportional to overflow velocity. We can derive a statement relationship between efficiency and the overflow velocity. So, that is efficiency is inversely proportional to 1 by V naught. That means less is the overflow velocity, more is the efficiency. More is the efficiency. So, how to reduce the velocity V naught? So, V naught is inversely proportional to BL. So, if you increase this BL, okay, if you increase the BL, then V naught will reduce. So, less is the V naught, more is the efficiency. So, we can reduce the surface area, we can reduce the overflow velocity V naught by increasing the surface area. By increasing the surface area. See here, efficiency is directly dependent on overflow rate and indirectly dependent on surface area. But efficiency is nowhere dependent on depth of the sedimentation tank. Efficiency is nowhere dependent on depth of the tank. Depth of the tank. It either depends on Vs, it depends on the diameter of the particle. Vs, if you see the formula of Vs is what? Vs is equal to G into S minus 1 d square 18 nu. So here, so this is constant, this is property of water, this is constant, specific gravity is also constant value, varying value is d. So the settling velocity is directly proportional to d square. Settling velocity is directly proportional to d square, whereas this overflow velocity is dependent on surface area. So nowhere in the efficiency term we are getting the depth of the tank. That means efficiency is independent. Efficiency is independent on the depth of the tank. So whatever be the depth of the tank you keep, so if proper surface area is provided, then the particle will settle. Otherwise the particle will not settle. Okay, otherwise the particle will not settle. So from this concept, to increase the surface area, what we do is we will make the sedimentation tank into different compartments. Okay, for example, this was the earlier sedimentation tank. Okay, now if you want to increase the surface area, what I will do, so the same flow I will send into some part of the flow into the top compartment of the sedimentation tank. I will make the sedimentation tank into different compartments, so that what is happening now, so here the flow is getting more surface area. Earlier the same flow has to get the surface area of this much only, but now when I am making it into compartments, some flow is moving into this, some flow is moving into this, some flow is moving into this. That means the surface area of the sedimentation tank has increased without altering the surface area, without altering the volume of the tank, simply by reducing the depth. This is called tube settlers. These are called, this concept is called tube settler. That means in order to enhance the efficiency of the sedimentation tank by making some kind of compartment kind of arrangement inside the sedimentation tank in order to increase the surface area, that kind of arrangement is called a tube settler. Tube settler is also a latest advancement in the sedimentation tank. Okay, tube settlers are the latest advancement in the sedimentation tank. So this is all about the sedimentation tank. The settlement of the particle inside the sedimentation tank. So there are different kinds of settlements. Okay, whatever the settlement we are discussing inside the plain sedimentation tank, we are analyzing using the Stokes law. Okay, we are analyzing using the Stokes law, and the assumption of the Stokes law is the particle settles discretely. What is meant by discrete? What is meant by discrete settlement? Discrete settlement means the particle settles independently without disturbing, without interfering any other particles. That is called discrete settlement. That is called discrete settlement. Okay, so the type of settling in plain sedimentation tank, the type of settling in plain sedimentation tank is considered as discrete settling, is considered as discrete settling. So, or we call this as type 1 settling. Type 1 settling. It is also called type 1 settling. So that is why we call this tank as type 1 settling tank. So that is why the plain sedimentation is called as type 1 settling tank. Type 1 settling tank. So this is another term of plain sedimentation tank. Okay, so what is discrete settling means? See, when a particle is settling in its own path, without disturbing any other particles movement is called discrete settling. It is called discrete settling. Okay. So this is all about the rectangular continuous flow type rectangular sedimentation tank or settling tank. So let us analyze and design the circular tank or vertical flow type sedimentation tank. Analysis and design of circular type vertical flow sedimentation tank. Type sedimentation tank. Okay, so how it looks like. First of all, let us see how a circular tank will looks like. So this is the plan. This is the plan of a circular tank. This is the plan of a circular tank. And if you see the elevation front view of a circular tank, this is the inflow into the sedimentation tank. This is the inflow into the sedimentation tank. This is the inflow line. Inflow pipe. This is inflow pipe. And the water will come out like this. So here, from here the water will enter into the sedimentation tank. From here the water will enter into the sedimentation tank. So this is a settling zone. So this is settling zone. This is settling zone. And here whatever the conical portion, so the conical portion is sludge zone. This is sludge zone. This is sludge zone. Okay. So this is flow velocity direction. Here if you take any particle, so the particle will have flow velocity in this direction and the settling velocity in this direction. Okay. Flow velocity is radially outward. So if you take the movement of the water, if you see in the plan, the particle is moving outward like this. This is velocity of flow. So this is velocity of flow. And the velocity of settlement will be vertically downwards. You can see it here. Velocity of the particle is velocity of flow in this direction and velocity of settlement in this direction. Okay, velocity of settlement in this direction. Now this is the diameter. This is the diameter of the circular tank. This is the diameter of the circular tank and this is the height of the circular tank. Height of the circular tank. This is the height of the circular tank. See, in vertical flow, if you see the vertical flow, this is vertical flow. In vertical flow type sedimentation tank, the flow is taking place in this direction. That means when the flow is taking place, the area of cross section of the sedimentation tank is increasing. When the flow is taking place, so from here the flow is entering into peripherally, it is moving along the circumference across the cross section, it is moving. When it is moving across the cross section, so this is the cross section for the first location. In the second location it has increased, third location it has increased. That means when the flow is advancing towards the outlet, this is the inlet, this is the outlet. From inlet to the outlet, the area of the cross section is increasing. When the area of the cross section is increasing, the velocity of flow reduces because here the discharge is constant everywhere. Whatever the discharge has entered in this zone, the same discharge will go here, the same discharge will go here. So discharge is constant, area is increasing. We know that Q is equal to AV. Okay, so if Q is constant, when the area is increasing, what happens to the velocity? Velocity of the flow decreases. In the rectangular sedimentation tank, Vf is constant. In rectangular sedimentation tank, Vf is constant. Okay, Vf is constant. That is why there the resultant is a straight line. So here Vf is constant. That means Vs is also constant for a particular size. That is why the propagation of the resultant is also a straight line. But in circular sedimentation tank, this Vf is not constant, it is varying. So the Vf in circular sedimentation tank is a decreasing value. So Vf, when it is moving away from the inlet towards the outlet, it is decreasing. But the Vs is constant here also. It is constant for a particular size of a sediment. So here both are constant, that is why the resultant is a straight line. Here this is a varying one, that is why, so it is varying of first degree, then the resultant will be varying of second degree. Okay, so that is why the resultant will be a square parabola. So the resultant velocity here it is in the particle movement. The resultant particle movement will be in a parabolic path. Okay, so as the value of Vf is changing, the particle settles in a parabolic path. So this is a parabolic path. Okay, so in rectangular tank the particle will settle in a straight line. In circular sedimentation tank the particle settles in a parabolic path because the velocity of flow is decreasing from the inlet to the outlet. Okay, now if you see the design part of the circular sedimentation tank, if you see, this is analysis, rest of the analysis are same, only the thing is the settlement of the particle changes. So Vf, what is Vs, everything is same for a circular sedimentation tank as well as rectangular sedimentation tank. So where it is varying, that we need to discuss. Okay. Now, design of a circular sedimentation tank. Here design means we need the volume. We need the volume of the circular sedimentation tank. So volume V is equal to d square into 0.785 H, 0.785 H plus 0.0011 D, 0.011 D, sorry, D, 0.011 D. See, actually, if you take a circle, you might think that it is like a cylindrical, it should be pi d square into H, but we need to take the conical zone, this sludge zone also. So including this sludge zone, the volume is this. Including the sludge zone, this is the volume of the circular sedimentation tank. This is the volume of the circular sedimentation tank. And if you want to determine the detention time, dt is equal to, we know that, volume by Q. So if you know the volume of the circular sedimentation tank, then we can find the dt using the formula dt is equal to volume by Q. And overflow rate, there in the rectangular sedimentation tank, what is V naught? V naught for rectangular sedimentation tank, V naught for rectangular tank is Q by BL. So that means surface area. This is called what? Surface area. Here, what is the surface area for this? What is the surface area of this? Q by the surface area. This is the surface area, plan area. That is pi d square by 4. So overflow rate calculation varies in circular sedimentation tank. It was Q by BL in rectangular sedimentation tank, whereas in circular sedimentation tank it is Q by pi d square by 4. There is another term called wear loading rate. So we call it as WLR. This is wear loading rate. So the wear loading rate, it is defined as the discharge which is coming out of what is the load you are applying on the wear. See, simple, I will explain what is wear loading rate. Let us erase this and then we can easily explain it by drawing a figure. Okay. If you take a rectangular tank, so this is the rectangular tank. So the flow which is going out of the tank, so this is the wear from which the flow will go out of the tank. So the location where the outflow is moving out of the tank, this is acting like a wear. This is the outlet. So this, how much discharge is passing through the outlet wear, that is called wear loading rate. The discharge passing through the outlet wear. So what is the dimension of this? This is B. For a rectangular tank, this is B. If you look at the circular tank, if you look at a circular tank, so this is a circular tank, this is the inlet. So the outlet is passing through the circumference of the outer dia, right? This is the location from where the outlet is passing through the tank. So now this is the discharge which is moving away from the tank at the outlet along the circumference. Along the circumference. So the wear loading rate is nothing but at the outlet, what is the discharge you are loading on it per unit area or per unit circumference, whatever it may be. So that is called wear loading rate. So wear loading rate is nothing but the discharge by length of the wear. Discharge upon length of wear. Length of wear. So if it is a rectangular tank, for rectangular tank, the length of wear is nothing but the width direction, dimension of the width of the sedimentation tank, that means Q by B. So we need to see what is acting like a wear. That length, it may be width. If the flow is taking place along the length, then length is the length of the wear. So from where the outflow is taking place, that dimension we need to take. Here for circular tank, it is equal to Q by pi into D. This is the length of the wear. Pi D is the length of the wear for circular tank. Okay. So this is all about the sedimentation tank. This is all about the sedimentation tank or settling tank. Plain settling tank, plain sedimentation tank. Now we are moving on to the next topic, that is sedimentation aided with coagulation. That is secondary sedimentation tank. We also call it as secondary sedimentation tank. In treatment of water, plain sedimentation tank is over. We are moving on to the next topic, that is secondary sedimentation tank. Sedimentation aided with coagulation, or we call it as this as secondary sedimentation tank. So why this is needed? Why the external help is needed to sedimentation tank? So the plain sedimentation tank is effective in removing the larger suspended particles, but it is poor in removing the fine suspended particles, colloidal particles and dissolved particles. The primary sedimentation tank or plain sedimentation tank is effective in removing larger suspended impurities. But this primary sedimentation tank is ineffective. It is ineffective in removal in removal of finer suspended impurity and colloidal and dissolved impurities. So to remove this, so to get a quality water, to get wholesome water, we need these impurities to be removed. For removing these impurities, we need an external source because its ability is not there to remove those particles. So we need some friend here to help us to remove those particles. Why these particles are not getting removed? Why these finer suspended impurities, colloidal impurities, dissolved impurities are not getting removed in a plain sedimentation tank is generally they are very fine in size. Okay, so their weight is not predominant. So their mass or weight, gravity, they are not that much affected by their weight, but they are affected by their charge. So all the finer particles can be removed by surface forces, not by body forces, because these finer particles during its travel in the sedimentation tank, so they will get wear and tear. That means they have to travel through the water because of this wear and tear. They generally carry negative charge on their surfaces, okay, because of the friction in the movement. So they generally carry a negative charge on their surfaces. Because of this negative charge, okay, they won't allow any particle. So all the finer particles will be negative charge. So if you want to settle them in sedimentation tank, sedimentation works on the principle of gravimetric technique. That means we want the particle to settle on its own weight. When this negatively charged finer particle, if it go and attract with another negatively charged particle, then only their size will increase. Are you getting me what I am saying? In water, in raw water, there is a finer particle and water present. So if you want to remove the finer particle, you need to bring all the finer particles together, and during this process its weight will increase so that they can get removed under gravity. In order to do this, so here this finer particle is also negatively charged, this finer particle is also negatively charged. How these two will come together? Because they repel each other, they won't come together. So what we need to do, because of this surface charge, they are stable in the fluid. They are not moving anywhere, they are not settling down, they are stable. They are standing stable in the fluid and it is moving to the next treatment unit. We don't want that. So that is why, so in order to remove these particles, first we need to do destabilization. We need to do destabilization. Destabilization is nothing but the charge neutralization. Destabilization means charge neutralization. Once you do destabilization, then we need to do agglomerization. Agglomerization means what? Bringing the particles together. So the two things we need to do here. One is destabilizing the particles, that is charge neutralization. Once the charge neutralization is over, we need to bring these particles together, that is agglomerization. These are the two things we need to do in order to remove the colloidal or finer suspended particles in the water. So how this happens, let us see. Okay, how this happens. I told you, so the colloidal particles or finer suspended particles, and colloidal particles are stable in water, due to surface charge surface charge and negligible weight. Negligible weight. To make them settle, so we need to destabilize the charge. We need to destabilize the charge. Destabilize the charge by charge neutralization. And increase the weight of the impurities by agglomerization. So for doing this thing, for destabilization and agglomerization, okay, for these things we add the coagulant. For performing these operations, we add the coagulant. Okay, we add the coagulant. So the colloidal particle, whenever we see a colloidal particle, majority of the colloidal particles are negatively charged particles. So these negatively charged particles, they present in the water. Okay, they present in the water. So some particles may have an affinity to attract the hydrogen ion present in the water. So may have a capability to attract the hydrogen ion inside the water. Okay, inside the water they react with H plus ions and form a strong layer. It's called Stern layer. Okay, so if you see the negatively charged particles, so all the negatively charged particles, so they will form a layer. All the negatively charged particles present in the water. So the hydrogen ion, the water is a dipolar molecule. So when it is getting a negatively charged particle, when it is finding some negatively charged particle, then it will offer a positive charge by H plus ion. So these negatively charged particles are being attracted by the hydrogen ion of water, and they form like a layer like this. This layer is called Stern layer. This layer is called Stern. This is called Stern layer. Okay, this layer is called Stern layer. And if there is any surplus charge, so either there may be surplus of negative charge or there may be surplus of positive charge. That surplus charge will take the outer layer, diffused layer. So whatever be the surplus charge which is present here, they will be taken place here. They will take this position. Okay, this layer is called diffused layer. This layer is called diffused layer. Okay, this is called diffused. This layer is called diffused layer. So this is called Stern layer and this is called diffused layer. And to break this layer, we need a potential. Okay, so to break this layer we need a potential that is called zeta potential. Here these are the particles where we need to go. So these are the negatively charged particles. They are just staying along with the water by doing friendship with water, as the water is dipolar. For bringing them down from the water, so our friend coagulant has to break this diffused layer and enter this Stern layer. So that energy needed to break this diffused layer is called zeta potential. So the energy needed, zeta potential. So the energy needed to break the diffused layer, is called zeta potential, and its value is 4 pi delta q, 4 pi delta into q, 4 pi delta q by d, 4 pi by d. So delta is thickness of the zone of influence of charge. Thickness, for example, so this is the charge, Stern layer. So if this is the, so the charge is maximum here and it gradually becomes zero when you reaching the diffused layer, boundary of the diffused layer. So delta is up to the diffused layer. What is the thickness of diffused layer? This is nothing but delta, thickness of diffused layer, thickness of diffused layer, and Q is the difference of charge. What is the charge? Charge in particle. What is the charge? And D is the dielectric constant of the medium. Dielectric constant of medium. So this is what is zeta potential. So with this potential is needed for a coagulant to reach the colloidal particles, So once it reached the colloidal particles, then it can do the charge neutralization. It can release this hydrogen molecule, and this coagulant will come and connect to this negatively charged particles, and now the charge neutralization takes place. And what happens, we will discuss what is the mechanism of the coagulant, how the coagulant works, how the coagulant will do all this procedure. We will discuss it in the next class. Thank you so much.